This is riveting video. I love when it starts like this. Okay, you go here, you come here. Full page view. All right. Well, since it's only you two guys here, I wasn't sure if I wanted to go into this or not, but I thought I could draw a picture that would sort of clarify the stuff we were talking about with interpolation. What I was saying was wrong, but what I'm saying now is right.
That's right. I completely forgot to send you my work from problem number 5 for linear interpolation.
Oh. Okay, so for a two-dimensional linear interpolation, there's the x and y, there's the independent variables, and then from there you have, let's say, this. So here are the 4 points on the surface. Okay, so I'm just trying to make it so it's general, and clearly what I was thinking before, I hadn't really drawn any pictures, and I was thinking like it's two sets of parallel lines, but that's not the case at all. And so you have this surface like this. Okay, and that is not a plane in general, and it also doesn't go along the actual surface, so the idea here is that this, let me do it as like a star or something. This is what we're trying to approximate, and the two ways of doing the interpolation so let me copy this so I can okay, so the first way you could do this interpolation is first interpolate along this line and this line, and then third interpolate along this line, and that would be your point. So that's one of the ways.
Yeah, with the star being the actual point,
yeah,
and the red point being our approximation.
Yes, exactly. And then the other way you could do it would be first do along this line and this line. So that would be here and here, and then do it along this line, and this would be our point. And those are not the same point in general.
Okay, yeah. So if you were doing it, for example, problem number 5, the first way, and then I was doing it the second way.
Yes.
Which is why we get 2 different results.
Yep, that's right.
Because the approximations are
Right. And the more, like the closer you are to having this be a parallelogram, I guess,
Yeah.
with the closer those are to being identical, depending on which way you go.
Yeah.
You know, but
like those approximations are going to be closer.
Yeah, right. If it's a parallelogram, they'll be the same.
Yeah.
But if it's really far from being a plane, then it's not going to be the same.
Yeah.
Okay. So that's that.
One last question.
Mhm.
Is there a rule of thumb about what approach to take? Like, for example,
Nope.
approach 1 or approach 2?
No,
Okay.
because there's no all those properties. There's no like reason to pick one as a first property and one as a second property or whatever. Yeah.
I see what you're saying. Yeah, at least at the point, at our point, when we're looking at the data, we can't really take bias one way or another.
Right. Exactly. Yep. So they're both equally just approximate, you know. Okay, so now what I want to do is we're done with what I think of as sort of like the first part of this class, which is all the first law stuff. I mean, we're going to keep using first law, but we're going to get into the second law next. So I just want to go back and do like a sort of a summary, a kind of complete outline of all the things we've talked about so far. Looking at it, I think we'll finish it today, but I'll just try to like annotate it a little bit and give you all this stuff in sort of a concise form. So this is an outline of everything before the second law of thermodynamics. And there are a couple of things in here, and I'll point those out when I get to them, that maybe there's just the one thing that I'm thinking of, but there's one thing that we didn't talk about, but I'm going to bring it up here just so you hear the word and talk about it in your notes. We did do a couple things related to it, but I don't think I gave this term. Okay, the first thing is like the introduction. That's where we talked about mostly pressure. And so we first talked about pressure, and the pressure equation that we used was that the pressure at the lower point minus the pressure at the higher point is equal to rho GH. This is for a static fluid. Rho is the density of the fluid. G is the acceleration of gravity, and H is the difference in heights. And we use that to do calculations with barometers and manometers. And then the second thing we talked about was work. And work can be work due to expansion or contraction of a gas. And in that case, to calculate the work, It's equal to the integral from state 1 to state 2 of P dV. And then second, work can also be done, added to the system or done by the system with rotating shafts or electric power. Both of those can come in or out, energy in or out of the system. And then the second thing we talked about after the introduction was the first law of thermodynamics for closed systems. And so that took this form: the change in energy is equal to Q minus W. Q is the heat added to the system. And W is the work done by the system. And so positive Q is adding energy to the system. Positive W is taking energy away from the system. And delta E is the change in internal energy plus the change in potential energy plus the change in kinetic energy. And these two are not always, but are often ignored. So here are some things we know about, simplifications we can make to this. The first one is if this is steady state, then the change in energy is equal to 0. Second, if we're doing this over a cycle means that at the end of the cycle, the state is the same as at the start of the cycle. So same thing, the change in energy is equal to 0. Second, so part B, the differential form of the first law. That is that dE dt is equal to Q dot minus W dot and the one common simplification for this one is if it's in steady state, the time derivative of the energy, system energy, is 0. So what I'm going to call the third category are the heat transfer equations. And the thing to remember about this is the signs from the heat transfer equations can't be, trusted with the first law. And really, you'd use this, I guess, with the differential form of the first law. So the signs you get out of the heat transfer equations, you then have to think about whether energy is being added to your system or removed from your system, and then use our usual sign convention. And there are 3 types of heat transfer. The first one is conduction. This equation is called Fourier's law. And it says Q dot is equal to negative Greek letter kappa times capital A times dt dx. Where this letter kappa is called the coefficient of thermal expansion. That's something you look up for a specific material. And often, the temperature gradient is going to be linear across whatever surface it's conducting through. So if you have a linear temperature gradient, then you don't have to do this as a differential equation. You can just treat it as Q dot is equal to negative kappa times the area times the change in temperature over the thickness, which I think that's the only, in any conduction problems you do in this class, I think that temperature always varies linear, so you can just jump right to that. So like if you're doing it for a window, that delta T is just the temperature at the outside minus the temperature at the inside, and the delta X is just the thickness of the window. Okay. Second is radiation. And that's the Stefan-Boltzmann equation. And there are actually two forms of this that we use. The first is for just the radiation emitted from a body. And that is that QE for emitted dot is equal to epsilon times sigma times AT to the fourth. This epsilon is the emissivity. Sigma is the Stefan-Boltzmann constant. E is the surface, A is the surface area of the object. And T is the temperature of the object. And that has to be on an absolute temperature scale. So probably Kelvin, but you could use Rankine too. I'll just put Kelvin. And then, so that's emitted from a body, but it doesn't say anything about the energy absorbed by the body. So that's sort of limited use. But you can also calculate the net radiation from a body if it's surrounded by a larger body. And so this net radiation is useful because then you're actually measuring how much energy is going in, how much is going out, and you can use that in equations. So this is the net radiation emitted from a body surrounded by a larger body. And that equation is QE dot is equal to, again, emissivity, epsilon, times the Stefan-Boltzmann constant, sigma, times A, and then times the quantity, temperature of the body to the fourth, minus the temperature of the surroundings to the fourth. And then after radiation, the last form of heat transfer is convection. And the formula for convection doesn't have a name. It's not like a scientific law. It's just sort of some stuff that you noticed, and you have to know, you have to take measurements of your setup. But the heat emitted by convection is equal to a lowercase h times A times the difference in temperature between the body and the fluid. This H is a catch-all. That's the thing that you have to determine experimentally. And A is the surface area that's exposed to the fluid. Okay, so this is all for the first law. We have the regular first law, the differential first law, and the heat transfer equations. And next we got into material property relationships, so equations of state. So this is going to include, the assumptions about incompressibility, the ideal gas law, and how to use tables. All that stuff is just relationships between properties. So material property relationships. So first, we talked a little bit about the PVT surface. Next, we talked about quality for materials at saturation. We call that lowercase x, and that's equal to the mass of the material that's in a vapor state divided by the total mass, which is the mass that's in vapor state plus the mass that's in liquid state. That has to be between 0 and 1. Where 0 would be all liquid and 1 would be all vapor. And you can use the quality to calculate the specific volume, specific internal energy, specific enthalpy, or specific entropy soon. So you can use this quality X to calculate lowercase v, u, h, or s for saturated materials with a mixed phase. And that formula is, if you call that property Q, the total Q is equal to X times that Q for vapor plus 1 minus X for Q for the liquid. Then next we introduced enthalpy. And as an extensive property, capital H is equal to capital U plus pressure times capital volume. And the specific enthalpy is the extensive divided by the mass, and that's equal to specific internal energy plus P times specific volume. And then we introduce the specific heats. C sub V is equal to the partial of U with respect to temperature with volume held constant. And C sub P is the partial of lowercase h with respect to T with pressure held constant. And then the last thing we talked about in this section on material property relationships was the simplified models, the simplified material models. The first one of those was incompressible. We'll always use that for fluids. Actually call that liquids. And we're going to assume that the specific volume is constant. But you want to look it up at the temperature that the temperature range that you're at. So look this up. Your temperature. The specific internal energy is assumed to be a function only of temperature. And because U only depends on temperature, Cp and Cv are the same thing. We'll just call them C. And that's equal to the total derivative du d temperature. And the second simplified model is the ideal gas model. And that's based on the ideal gas law that for us, it has the form P times specific volume is equal to RT. Where this R is the universal gas constant divided by the molar mass of the gas. For an ideal gas, the specific internal energy is only a function of temperature. And so that means CV is just dUd temperature, just like it was for incompressible. And since H is U plus PV, and PV is equal to RT, you can see by substituting the ideal gas law that C sub P is just CV plus R. Okay, so that's the end of the material property relationships. So we had the introduction. We talked about the first law of thermodynamics. Talked about these property relationships. Oh, and actually, that's not the end because no, that's not even close to the end. Sorry. So ideal gas law, and then we are into simplify incompressible. Let's see. Incompressible ideal gas.
Yeah, we went over conservation of mass next, wasn't it?
Yeah, well, in a second we'll get to that. So we still have to, okay, so the next one I want to talk about, this is the one that, so number 3, this is the one that we didn't use this term, but we did do a couple problems that were like this, but this is polytropic processes. And those are processes of the form P times the extensive volume to the R is a constant. And you can rearrange this as pressure as a function of volume is equal to some constant times V to the negative R. And the most useful fact about processes like this is that the work, since you have pressure as a function of volume, you can use the integral of P dV relationship to calculate the work as the integral from state 1 to state 2 of C V to the minus R dV. So if you have a polytropic process, you could just calculate the work directly.
Quick question.
Yeah.
What kind of processes, or I should say, what kind of examples do we see polytropic processes? Using the ideal gas law.
Yeah. Well, ideal gas law. Let's see. If you have yeah, I can't think of any examples. I can get you some, but the ideal gas law is actually a polytropic process in the case of no temperature change.
Okay.
Then that would be, so if temperature is constant, then set R equal to 1, and that's the ideal gas law. But there have been a couple of problems, I think, in assignments that have had that form.
Yeah. I've seen the form,
yeah.
Mathematically,
right?
Just trying to think when you apply.
Yeah, when.
Yeah, what kind of system?
Yeah, like when, right.
I assume though, yeah, there are plenty of cases where the ideal gas law doesn't necessarily apply.
Right. I guess that's probably right. I guess it's probably in cases where the ideal gas law doesn't work very well because you have too high a pressure, too low a temperature or something, and then.
Yeah. And then I assume this R value would be like a measured relationship.
Exactly. Yes, exactly.
Okay.
Then it's something that you do experimentally or whatever, and yeah, and you know for the ideal gas law for an isothermal case, R would be equal to 1. For all the examples we've seen in the book, R is equal to like 1 point something, you know. So there are just cases where that increases a little bit. Maybe it's cases where the temperature is changing, but you know something about you can measure just a connection between those two.
Oh yeah, like with an adiabatic system where there's the change happens fast enough that the temperature or no heat comes out.
Something like that. Yes, that is my guess. Yes,
okay,
that's right. Polytropic processes. So next is tables. So this is an important one. And for tables, the main thing that, I mean, you have to know how to look stuff up. I guess let's get in here that for compressed liquid, or superheated vapor, you need pressure and temperature to look up properties. At saturation, you only need pressure or temperature to look up the properties. And to use these, we usually have to use interpolation. So that has the form f of x is f of x1 plus f of x2 minus f of x1 divided by x2 minus x1. And then that fraction is multiplied by x minus x1. Where x is the known property, and f is the desired property. For saturated materials, so at saturation, you only need one interpolation. If you're not at saturation, then you need to do it in 3 steps. And those are, first calculate F of X, Y1, then calculate F of X, Y2, and then finally F of X, Y. And in this case, this is where X and Y are the given properties, and F is the desired property. Any questions about any of that? Okay, so that's the end of material property relationships. And so now we're going on to control volumes. This was number 3, I think. Okay, so now number 4. And this is control volume analysis. The first thing we talked about was the continuity equation, mass balance equation. You can think of that 2 ways. I guess we're doing, for control volumes, we're doing everything as a differential form. So we're going to use the form dm dt for the control volume is equal to the mass flow rate coming in minus the mass flow rate going out. And there are 2 things that come up quite a bit that are useful for this. The first one is calculating the mass flow rate at the inlet or exit. So m dot is equal to the area of the opening times the speed of the fluid, that's the average speed, divided by the specific volume, or multiplied by the density. Capital V is the average flow speed. And then area and specific volume. The second thing that's useful is if you're in steady state, the mdt of the control volume is 0. And so this equation simplifies to just m dot coming in at the inlet is equal to m dot at the exit. And then besides mass balance, the only other control volume equation that we've used is the first law. So B is the first law for control volumes. And that's that messy equation, dE dt for the control volume is equal to Q dot for the control volume minus W dot for the control volume plus M dot coming in times the quantity HI plus VI squared over 2 plus GZI, and then minus all that same stuff at the exit. So M dot at the exit times the quantity HE plus VE squared over 2 plus GZE. And then we talked about the 5 devices. So the first one was nozzles and diffusers. So 2 of these we did in pairs and 1 we did by itself. In its most simplified form, we assumed steady state fast flow through the device and rigid walls of the device. So the steady state gave us that dE dt was equal to 0. The fast flow said no heat transfer through the walls. And the rigid walls said no work done by the device. And then we also assume that there's no change in height. And so you get a form that is, you can write it as HI minus HE is equal to 1/2 times the speed at the exit squared minus the speed at the inlet squared. And these sides of the equation are, so for these sides to be positive, we would need the speed to be higher at the exit and the enthalpy to be higher at the inlet. And so these are positive for a nozzle. And negative for a diffuser. Then second, we talked about turbines. And in its most simplified form. So remember that depending on what the question gives you, you might not be cutting out all of these terms, but this is sort of the term that gives you the best sense of what this thing, how this thing is intended to work, you know. But nothing has perfect resistance to heat transfer, and nothing's perfectly steady state. But in its most simplified form, it's steady state. And so dE dt is 0. There's no heat transfer. The change in kinetic energy, there is some, but it's small compared to the other stuff. And there's no change in potential energy. And so you get a form that says W dot for the control volume is equal to M dot times HI minus HE. And so actually, when I say steady state up here, gives you that dE dt is equal to 0. It also says that Mi dot is equal to Me dot, and we'll just call that M dot. And then the third category is compressors and pumps. So both can increase the pressure. Compressors are for gases and pumps are for liquids. If you're increasing pressure, this is the most simplified form. Assume it's steady state. And so dE dt is 0. And Mi dot and Me dot are just M dot. Assume there's no heat transfer. If we're talking about pumps increasing pressure, then we're going to assume that there's no change in height. So the change in GZ is 0. And also the change in speed is 0. And so you get a form that W dot for the control volume is equal to m dot times hi minus he. And both sides of this equation are negative. Then there's also applications of pumps where you're not using it to increase the pressure, you're using it to lift a liquid up some distance. So to use a pump to lift a liquid, for the simplified form, we're going to assume steady state. So d dt is 0. And mi dot and me dot are just m dot. We're going to assume q dot is 0. We're going to assume that there's no change in pressure, and so there's no change in enthalpy. So delta H is 0. We're going to assume that there's no change in speed. And so you end up with a form that W for the control volume, W dot, is equal to m dot times the quantity GZ inlet minus GZ exit. And both sides of this equation are 0. Not 0, negative. Okay, so that's sort of where we are in the class right now. Anybody have any questions about any of this stuff that we went over? I think this summary is sort of helpful. It might not be a bad idea while you're trying to, like, there's certain classes where you have very little, like, it's hard to learn the skills that you have to learn, but you don't have to remember much information. And then there's some classes where there's a lot of information and not as many skills, you know. This one has a fair amount of information, and it means that it's hard to sort of keep it straight in your head. And so I think it might not be a bad idea to just print something like this out and just have it in front of you as you work on these problems and as you start to get ready for the first test, you know. The first test is going to be, I forget whether it's Tuesday or Thursday, but it's in 2 weeks, either 2 weeks from Tuesday or 2 weeks from today. So I'm not going to have any second law stuff on it. So all of this stuff, that's sort of like a study guide for the first exam. So as you get ready, looking back over like the daily assignments and the weekly assignments that I've given so far, having that thing in front of you, I think would be a good idea.
Is there any material that, or I should say example problems from the outlines that we should be looking at?
I'm sure there are, you know, I've not gone through and like looked for for good problems. If you send me an email, I could try to find some, but I think for the most part, if you just go to those sections and pick out problems, like it's all just practice getting kind of from the few things you know and the one thing you want, just rearranging it and getting it in the right form. But yeah, I think it would be a good idea to like doing problems from the Shams outlines would be helpful, I think.
That's what I figured. I just haven't worked through any problems
Yeah.
on here.
But I think you can also just get by like, so you've done the daily assignments once or whatever. I think it's a good idea to actually go through those again, like a little bit later, try to do them again without looking at the solutions and stuff, and just make sure it's solidified. The problems I'm going to give on tests are, following those same kind of thought processes.
Okay.
So I think with just the problems I've assigned, like you could understand this stuff, be ready for the test well, Any other questions? Okay, well, that's it for today. So have a good weekend. And so Tuesday we'll start talking about the second law.
Okay. Yep. So going over entropy.
Entropy, yeah.